Okay, and so these are the different harmonics then that we can deal with a vibrating string. And so the question though is, how can we write the wavelength and the frequency in terms of given quantities? Any questions so far? Okay, so this is our, and by the way, I always thought this was kind of obvious, but I found out after grading a lot of exams in Physics 208B over the years that this isn't obvious, that this is the equation for standing waves, and the other one is the equation for traveling waves. And so on quizzes and exams, I think I'm getting a lot of equation hunters who go, well, okay, I'm going to take that equation, I'm going to plug it in. 50-50, no, I hope I'm right, type of thing, rather than really understanding which equation relates to what. So this is our standing wave equation. And we want to make sure that this is completely understood as being different from the traveling wave equation. Remember, we just derived the traveling wave equation by taking two traveling waves that are moving in opposite directions to get the standing wave equation. But our traveling wave equation is y equals a times the sine of kx minus omega t plus phi. Or this could be a plus, depending on whether it's motion to the left or to the right. So we want to be absolutely clear as to when we use this and when we use that. Absolutely clear. Don't want there to be any confusion about that. And so you need to make sure that you're not just randomly grabbing equations and trying to make them work. All right, so how do we get the k? Well, if you'll recall, the k here is our wave number. That's 2 pi over lambda. And so we have n possible lambda values depending on which harmonic we're dealing with. And so n then is our what we call our harmonic number. And so let's just see if we can find a pattern. For this one, this is n equals 1. Then what part of a wavelength is this if we're going from node to node? How much of it, of a wavelength is that? Is that a whole wavelength? Half. Good. Because if you extend this along, this is just 180. This brings us back to our original position there, 360. And so you can say then that 2L equals lambda 1. Okay. Twice the length is the wavelength, which is lambda 1. What about for the second harmonic? This is n equals 2. This is also called the first overtone. This is also called the fundamental. I'm giving you these terms. I'm not necessarily going to be using them a lot because it's confusing to go back and forth between them. But a lot of times if you're talking about, well, that's the fundamental, you're talking about the lowest possible frequency and the longest possible wavelength. And then anything else that's added on to that is usually just changing the shape of the waveform in music theory. And so you have a basic frequency, but then what makes middle C sound different on a tuba than it does on a flute is the amplitude of the overtones, the amplitude of all of these higher harmonics. So that's why there's a difference then in the terminology. But in terms of the actual equations that we use, I think it's much simpler to use the harmonic notation. Okay, so this is n equals 2, and so here L equals lambda. So lambda 2 equals L. Lambda 1 equals 2L. Maybe not enough to get a pattern yet. Now how do we start drawing the rest of these harmonics? And why am I drawing them this way when the thing is doing this all the time? Well, again, what we're doing is we're basically looking at a strobe of this. So imagine it goes down and up. You take a bright flash of light, down and up, take a bright flash of light, down and up. So we're not looking at the cosine omega t part. We're looking at this thing every time it goes through one complete period and is at that same point again when we're looking at the sine kx part. So that's what I'm drawing here. So here I go from node to node to node. Okay? And so I just count how many times I do that. Okay? So this is n equals 1, 2, 3. Okay, so it's simple. You just think of it that way. Each time you add in an extra half a wavelength, you're going up by one harmonic because you're satisfying the new boundary conditions. Remember, the boundary conditions to produce constructive interference, sine wave harmonics that have nodes at the endpoints. Okay, so for this one, L is still the same. So how does that relate to lambda 3? Well, this is 1 half, 1, 1 and a half. Okay, so this is going to be 3 halves lambda 3 L equals, 2/3 of lambda 3. Okay, because this is going to be one wavelength, this half, 1, 1 and a half wavelengths equals L. So lambda equals 2/3. Three halves wavelengths is the length L, and so therefore lambda is 2/3 L. And so if we want to do this one more time, 1, 2, 3, 4. This would be n equals 4. That's our fourth harmonic, or our third overtone. And so in this case then, you could say that 2 lambda 4 equals L. Okay? Or lambda 4 equals L over 2. Okay, so, and we could keep going, but I think we've got enough here to find a pattern. We're looking for something that involves n. This is n equals 2. This is n equals 3. N equals 4. Does anybody see a general pattern for lambda n?
2 times L minus 1 over n.
2 times
L minus 1.
well, L minus 1? Or just L?
Yeah, 2 open parentheses, L minus 1 over n.
What about 2L over n? Then if n equals 1, we've got 2L. N equals 2, we've got 2L over 2. Then is a 2. Okay, so that's L. Here, this is for n equals 3, this is 2L over 3. Does that look like it's fitting? And this is going to be 2L over 4. Okay, so this looks good then for lambda n. And so this is going to be our general condition then for the equation for the wavelength in terms of the harmonic number. Once we've got that, then we can write what k is. So Kn then is going to be 2 pi divided by 2L over n. So that's just n pi over L. So that's an expression then for our wave number for the nth harmonic. Okay, so now we can write this, y is equal to 2a. Now a is the original amplitude of either wave, but we could just call it a prime now if we want. Unless we're interested in the original wavelengths of the waves, we can just think of this as being the new maximum amplitude of our wave. Call that a prime, and not worry about the fact that it's 2 times a. Times the sine of n pi x over L times the cosine of omega t. Okay, so we're getting closer. But we also need some kind of an expression for omega. How are we going to get that? Well, let's go back to frequency times wavelength equals wave velocity. Then, what we can see here is that the frequency of the nth harmonic is going to be the velocity divided by lambda n. You see that? So, what this is telling us then, if the wavelength is cut in half, the frequency would be double. So does everybody see that's what's happening when we're going from the n equals 1 harmonic to the first overtone, or the second harmonic, is that we're cutting the wavelength in half, but by doing that, we're doubling the frequency. I'll bring in some demos for this next time. I don't have it right now, but you'll be able to see this. That's sometimes called an octave higher. If you go doubling the frequency, it's called an octave higher. And so we could rewrite then this as being the square root of the tension in the string divided by the mass gradient length divided by 2L over n. Okay? Just using the fact that we have lambda n is in there. So we use lambda n to get kn, but here we're using lambda n to get the frequency of the nth harmonic. Okay? And so this is going to equal square n times the square root of the tension in the string divided by the mass gradient length divided by 2L. Okay, but what is the frequency of the first harmonic? F1 is just equal to V divided by 2L, or the square root of F over mu divided by 2L. So this is just equal to n times F1, where this is the frequency of the fundamentals. So what we're going to see then in lab next week is that once you find the fundamental, then you'll be able to get different resonant frequencies, but they'll all be multiples of the fundamental. And so then omega n is going to be 2 pi times Fn. So now we finally have an expression for omega n in here. So omega n, we'll write this in as a prime times the sine of n pi x over L times the cosine of, and then here, we've got 2 pi times Fn, that's going to be 2 pi times the square root of the tension divided by the mass gradient length divided by 2L. That gives us over here the cosine of, well, omega is 2 pi times the frequency, so it's going to be 2 pi times square string divided by the mass per unit length divided by 2L with an N out of it. And so that's finally cosine, the 2's cancel, of n pi square root of tension divided by mu divided by L. Sine, and there's a T in there. Sine of n pi x over L. Or we could just write this as the velocity of the wave motion. So that would be a prime sine n pi x over L cosine n pi v over L times t. And this gives us an expression then for the amplitude of the nth harmonic at any point in space and time. So I'll write that again over on this one. This is kind of our final result for this. Y prime, a prime sine n pi x over L cosine n pi v over L times t. And so we should be able then to identify for any standing wave, say this would be n equals 2, should be able to go to this point of x and then wait a certain amount of time t and find the y prime at that point. That's basically what we're doing. Okay, so I could go farther with that, but I want to leave enough time for us to start working on our in-class activity. That won't be on standing wave. I want this to have a little bit of a chance to sink in. Are there any questions? And so a lot of this was just a derivation, but if you can start with something like this, this gives you something that gives you some important information about which harmonic frequencies you can get in a standing wave pattern. And this gives you the associated wavelengths of those standing wave patterns. So those are the two kind of critical points. And then this equation here I would give you if you needed to use it for a quiz or exam. I wouldn't expect you to derive it. All right, so on to our in-class activity. Now, for in-class activity, you are welcome to work in groups. That's just fine. And I'm going to ask that you turn this in online so that I don't have some of them coming in. But I don't want to rush you, and so I'll give you the rest of the day to work on this if you don't finish it. That basically what we have here is kind of an interesting transverse wave problem. Here, our transverse waves have a wave speed, 8 meters per second, amplitude 7 centimeters, wavelength 0.32 meters. The waves are traveling in the negative x direction. And at time equals 0, the x equals 0 end of the string has 0 displacement and is moving in the positive direction. Now the reason why this information is given to you here is so that you can determine the phase angle. Okay, so if we know what the initial conditions are of a point in the medium at time equals 0, we can tell what kind of a sine wave we're dealing with. That's moving in the negative x direction. So pictures are always helpful. It'll look something like this. Here is y equals the amplitude. This is your x-axis here, and this is the velocity of wave motion going to the left. Okay. And so what this is telling us then is that this particle in the medium is moving up in the positive y direction at time equals 0. So that tells me I've drawn the sine function right. If I had told you, though, that it's moving in the negative y direction, if I said negative, then the only thing that would be consistent with that would be this plot of the wave. Because, think about it for a moment, when this wave is at x equals 0, at the next moment, this part of the wave will be there, right? Because it's moving to the right. So that means that it would be moving in the, as this thing moves up, then this point here will move to there, and that point will move down. Whereas here, as this point moves to here, a second later, this point is moving up. Okay, so that is the argument that we're using to tell us that the phase angle is what? 0. Good. Remember, when you don't know the answer, just say 0. You're going to be right about half the time. So the phase angle is 0. So I set it up so the phase angle is 0. But I want you to be clear that if I had said this differently, then you'd have a phase angle of pi radians. Okay, because then you'd be talking about a negative sine function, and that would, at the next moment, be moving in the down direction. When this part of the wave gets to there, then it would be going down. So that would tell you that your phase angle would be either plus or minus pi. So that part should be helpful. And then we want to write the wave equation, find the transverse displacement of the wave at those two different values. Then in part C, how much time elapses until the particle next has 0 displacement. Okay, so that's going to be an interesting thing. What you're going to need to do here is look at the argument and to get it equal to 0, for this to be 0, that means that kx plus omega t has to be equal to what?
0. No, 1.
What, did I hear something with pi in it? No. Pi would work. Well, what about, it may not be just 1 times pi, though. It could be 2 pi, 3 pi, 4 pi, 5 pi. So we're going to have to, we don't know, because the kx and the omega t, these could be any values for x and t. So we move along and we wait. We don't know how many complete cycles we've gone through. And so we need to find n. Once you've found n, then round up to the next highest integer and solve for the time. You following what I just said? Once you've found n from this, this is kx plus omega t. Say this was 6.27 pi. Then set this equal to 7 pi and solve for the time at that value for x. If this were minus omega t, you'd round down. Because then this would be getting smaller. You'd be getting an integer multiples of pi, but it would be getting smaller as time gets bigger. So then you'd round down. If we're 6.5, you'd round down to 6. But because it's kx plus omega t, you're going to want to round up. And once you round up to the next integer, then plug in the value for x that's given and solve for t. And so that's going to be the time when we get the next 0 displacement. Okay, so you may need to think about that, play with it a little bit. We will have an embedded tutor that will be helping us, but they still haven't got her signed up yet, so it'll be me helping you. And just go ahead and break up into groups and whatever you feel comfortable with. Find somebody that looks like they might be a good study partner, and go ahead, and you can get started with this, and then I'll fill out something so that you can upload this by 11:59 this evening.